Act 2 of this workshop, hopefully at some later time in the future. That said, we have tried to optimize the program of the workshop for the online format and leave ample time for discussions, both between the talks and after the talks. A quick overview. We will, in the course of this week, have 4 review talks on topics that are relevant for the Celestial Holography program and several technical talks. These will be grouped in topical sessions, with each day ending in a longer discussion session. There we will have additional panelists, which will kick off with a short presentation, and then we'll be joined by the speakers of the day to receive questions from every one of you. And it will hopefully be a very lively informal discussion. Quick reminder, the review talks will be 50 minutes plus 10 minutes questions. The technical talks are 30 plus 10, and then the panel presentation will be 10 minutes. The talks will in principle be recorded and later be posted on the Corfu website. So if you're a speaker and you do not want to be recorded or the talk be shared, please let us know in advance. Also, unless otherwise requested by the speakers, questions can be raised at any time during the talks, between the talks. For this, please use the raise hands button on Zoom and wait to be called upon by the chairman or woman. Okay, now we can get started. So the focus of today's session is CFD aspects of celestial holography. And it is my pleasure to introduce our first speaker, Miguel Paulos, from École Normale Supérieure de Paris, who will review for us the CFD Bootstrap.
Okay, let me share the screen. Okay, so everyone can see?
Yes.
Yeah. Okay, so thanks a lot for inviting me to give this review talk. It's too bad that we cannot all be enjoying the sunshine in Corfu, but hopefully in some other edition we'll be able to. So I was asked to give a review talk on the Conformal Bootstrap, so I will give a very limited review, focusing on a few topics that are dear to my heart. I try to give a few references, well, give names of people who have been working in these subjects, but I've missed many, I'm sure. So if there are people in the audience who are not happy, please complain. And you can always ask me for references later on. Also, please don't hesitate to ask me any questions during the talk. Okay, so I'm going to talk about the Conformal Bootstrap. So what is the Conformal Bootstrap? So this is a set of ideas, a set of methods, and also tools, various kinds, analytic, numeric, and computational, that allows us to both constrain and determine the data that defines the CFD, and also observables in CFD. So what the basic philosophy of the Bootstrap, what is it? So it's a relation between these two things. So the CFD data, which are charges of operators, and by charges, this includes all the charges under the symmetry groups, all the quantum numbers of local operators and other quantities that might define non-local operators in the theory, how these operators couple amongst each other, both local and non-local, and so on. So all the basic ingredients. On the other side, we have the observables, and basically the observables in the QFT are simply some expectation values of both local and non-local operators in some suitable states, which usually is the vacuum, but you can take some other interesting states like a thermal background or whatnot. And the idea is that these quantities, they are related by various kinds of OPEs. I'm calling them OPEs. Maybe in certain contexts it would make more sense to call them something else, but okay. Roughly speaking, there are ways to expand these observables in terms of the CFD data, and this can be done in various ways. And so demanding consistency of all these different ways in which you have to relate these two things, it gives you constraints on both sides, on the data and the observables. So in practice, these relations, they turn into into specific crossing equations. I'm going to call them crossing equations. And our job then is to understand these crossing equations and what they imply both for the observables and for the CFD data. So a different way of thinking about the Bootstrap is that it involves the study of what we may call, roughly speaking, the kinematics and dynamics, or how these things talk to each other. So on the kinematic side, you could put defining interesting observables in the theory, how to, given these observables, how do you formulate these crossing equations that I mentioned? What are basic constraints arising from unitarity on the CFD data and on these observables? How can we compute, later on we'll see conformal blocks, so how do we compute these, and so on. So how do you build all these necessary ingredients? And then the dynamics is, how do you actually extract information and constraints by the crossing equations and kinematic restrictions on the CFD data. And really one informs the other, because of course you need all this basic kinematic data in order to set up the dynamical problem. But sometimes also the dynamics, it can tell you, or it can give you clues on how to better formulate the problem, how to better formulate the constraints of crossing, for instance, what I would call kinematics, in a way which is more enlightening. So it's really a dialogue between these two things. So now, after all this fancy talk, in practice, the Bootstrap program has focused on essentially one of the simplest of observables, which are 4-point vacuum correlators of local operators. And so this will also be essentially the main focus of what I will speak about. So for instance, if we have a correlator of 4 identical scalar operators, you can write them, as everyone should know here, in terms of some function of conformally invariant cross ratios, Z and Z bar. And so in this simple case, using unitarity and the operator product expansion, it will allow us to formulate some constraints involving positive quantities. So this is why this case has been very useful and has gotten us a lot of mileage, because you get this positivity. And positivity is really crucial in the way that we understand the Bootstrap right now, in the way in which we can get the results. And well, this reduces its scope, because there are many observables that you might want to bootstrap or to understand where this positivity is actually not manifest. In fact, if you just consider any other higher point function, then you will not get positivity, and so you don't know how to extract information in a useful way. So there are some formulations of the Bootstrap that allow us to do away with the positivity, but they are really underdeveloped. And so this is clearly a front where we need to advance. And it's really essential for studying even setups where you don't have unitarity, which is very useful and very important in the context of statistical physics. But also the moment that you start including non-local operators like defects or interfaces in the theory, then the crossing equations that you get, they don't have manifest positivity. So you need some other methods. Also, as I said, I mean, when you go to higher point correlators, usually people ignore this because they say, well, if I understand all 4-point functions, then I can construct any higher point correlators. But maybe this is a mistake, because maybe it might be more economical to study higher point correlators of the same field instead of considering 4-point functions of ever more complicated fields. Yeah, so there's been almost no work done on this front, and probably this might be a mistake. Okay, so let me start this section, what I would call dynamics from kinematics, which is a bit more the usual approach to the Bootstrap. So what are the basic kinematics? So let us discuss then local operators. The local operators, they are characterized by some charges in the overall symmetry group of the theory, which is usually the product of some possibly supersymmetric conformal group with some other global symmetry. So if you look at 2-point functions, then these are just uniquely fixed once and for all by conformal symmetry. 3-point functions are a bit more interesting. In this case, they are fixed only up to a finite set of couplings, which I call OPE coefficients. So for instance, if you take 2 scalars in a spinning field, there's one coefficient, but in general, once your operators have spin, so for instance, if you have three stress tensors, in this case, for instance, there are three independent OPE couplings. And in general, so when you have more spins, there will be more numbers. But it's always a finite number. And so when you consider 4-point correlators of, in general, operators carrying some charges like spin, you can always use conformal symmetry to expand this into some bases of tensor structures. So these are just some kinematic objects that you can compute once and for all. And then there are some independent dynamical functions. So people can see my mouse when I move it, right?
Yeah.
Yep.
It's
okay.
not visible.
So these functions, these kinematic functions, they admit using the OP some expansions. These expansions will involve conformal blocks, which capture the contributions of primaries and towers of descendants in the OP. So for one of these generic functions, this expansion takes this form. So in general, there are multiple OP coefficients associated with a given operator, as I said, and these guys, they talk to each other. And each OP coefficient comes with its associated tensor structure. So they talk to each other in this object, which is a conformal block, which depends both on the specific 4-point function, on the specific, on this index A here, which labels the different 4-point tensor structures. And it also depends on these different OPE couplings. It depends on the data of the external operators, and it depends on the data of the internal operator. So it depends on a lot of things. But in the end, it's a purely kinematical object that you can just compute once and for all. Of course, this is easier said than done. Actually, computing these conformal blocks efficiently was for a long time a major stumbling block in making progress in the conformal bootstrap, especially when you add spin, when the external operators have spin, because then you can get very complicated spin representations being exchanged. Or if you have supersymmetry, it's also complicated to work out the consequences of supersymmetry and what it implies for the conformal blocks. So in 3D, at least without supersymmetry, the problem is basically completely solved, and there's even an efficient computational package available that will allow you to compute conformal blocks at the crossing symmetric point and its Taylor expansion to any order that you want for arbitrary spin representation. In 4 dimensions, basically, it's also solved because we know how to express all the blocks in terms of some seed blocks, and these seed conformal blocks are also known. There's also a package for computing them. Now, in general space-time dimension, the problem is in principle solved. In principle, we know how to get everything because there's some technology called weight shifting operators that allows us to obtain these conformal blocks in terms of some easier ones. But in practice, there's a lot of work that has to be done. Whenever you're trying to solve a specific problem, these things, they have to be computed almost from scratch. So here I put a bunch of names of people that worked on conformal blocks in these various settings, but again, there's many names missing here. And so this is for 4 points. The minute that you go to higher points, then there's almost no results available, actually. There's almost nothing that is known about conformal blocks for higher point correlators. Okay, so the next step is formulating crossing equations. So crossing equation is just the statement that you can use the OP in 2 different ways, and it has to match. Okay, so in this simple case that we're examining here of the 4-point function, it's sufficient to consider these 2 channels, the S and T channels. And so equating the OP expansions leads to an equation, which I call the crossing equation. So what does the crossing equation involve? So it involves the difference of conformal blocks between the S channel and the T channel. Delta and L are the quantum numbers of the exchange operator. So in this case, this very simple case where the external operators are scalars, the interesting quantum numbers that appear are simply the scaling dimension and the spin. There's only one spin quantum number because the fields, they have to transform into traceless symmetric representation. And since we've done the OP twice, we get this OP coefficient squared. Okay, so finally we have these constraints here. So the sum over states runs over scaling dimensions larger than some delta UL. So basically this is because of unitarity restrictions. Depending on spin, not all values of delta are allowed. So this is the case, that was the case for a single scalar correlator. In general, you want to consider constraints for a collection of correlators where you consider many external scalar fields. And the point is that each crossing equation that you get will always be some quadratic constraint on the OPE coefficients. Okay, so if you consider just scalar operators as external legs, it turns out that in the end, the full collection of crossing constraints can be written as some kind of internal product between some vectors of OPE coefficients against some matrices, these curly Fs. Okay, there are several matrices labeled by this index P. The matrices, they know about the quantum numbers of the exchanged operator, which again is just only depends on scaling dimension and spin. And so this vector of OPE coefficient tells you how a given exchange operator couples to all the external states. Okay. So this is the general form when you have a collection of correlation functions. And okay, here I considered external scalars, but you can imagine that there are some more complicated generalizations of this when you have general spinning representations on the external legs. The point is that you always have quadratic equations on these OPE coefficients. Okay, this is really what's crucial. So let me go back to the simplest example. So we want to check, consider, let us suppose that we restrict the quantum numbers that can be exchanged to some set, which I call S. And now we ask, are there solutions to the crossing equation? Okay, are there any consistent solutions? So what we do is that we make these assumptions and then we try to get the contradiction with this equation. And these contradictions will be possible because these coefficients lambda squared, they are positive. They are positive for unitary theories, okay, because the lambdas can be chosen real. And to obtain these contradictions, we will have to construct certain linear functionals which have good positivity properties. These linear functionals will act on this equation and will give us the contradiction. So I formulate this as what I call the feasibility problem. So let us choose some set S where my quantum numbers live. And then I ask, does there exist any linear functional omega satisfying the following positivity conditions, so that omega, when it acts on these Fs for all the quantum numbers in this set, it should be non-negative. And when it acts on the identity contribution, it should be strictly positive. So if any such functional exists satisfying these constraints, then it's easy to see that there can be no solution to the crossing equation. Okay, because we write, this is the left-hand side of the crossing equation. We act with the functional here. It's a linear functional, so it just goes through. And then you just use these positivity conditions, and you find that it's non-negative, that it's positive. It's strictly positive, and so it can never be zero. So this is the feasibility problem. So once you restrict this set, if you can find this function, then you rule out that set. Questions about this?
Yeah, maybe I can ask a question while other people maybe raise their hands to ask more. So you said before that you will mention at the end something about non-unitary theories, but maybe I can ask at this point. Here, all these inequalities that you can write and the conditions that you can impose, they really depend upon the theory being unitary. So how can you constrain, how can you get constraints in, is there anything known or developed for non-unitary theories?
Yes, so for non-unitary theories, you have to take a different perspective. Here we are trying to get bounds on the allowed region, on the allowed sets of quantum numbers, okay? This will not be possible for non-unitary theories. However, what we can do is you can assume that you can make this set S very sparse, okay? So here what we have in mind is sets S which are very large. The restrictions are very mild. The restrictions are something like, let us assume that the scaling dimension of the first scalar is larger than X. That's it. But let us assume that instead of that, you say, no, I'm going to try to find a solution to crossing where there's only a handful of operators with dimensions lying in some ranges. There you might be able to say something even for the non-unitary case. Okay, basically, this is a linear equation. So the intuition is as follows. This is a linear equation. Okay, and the reason why you get bounds in the unitary case is that this is a linear equation with positive coefficients. And so you might not be able to find a solution if you have positive coefficients. In the non-unitary case, these coefficients are real, so in principle, you can always find a solution. However, you might not be able to find solutions which are too sparse. So if you take these, if you evaluate this equation, say at a set of n points, you might be able that you can ask the question, can I find a solution which only has n/2 operators? And this question actually has nothing to do with unitarity. Either it has a solution or it does not have a solution. The coefficients might come out positive or negative. And so this is how you might be able to bootstrap specific non-unitary theories, but you won't be able to get bounds. So yeah, this is very quick. I'm not sure if this was helpful, but the key is to use sparsity. I'll mention this a bit later.
Does this, if you solve the equations, that doesn't exhaust the constraints of crossing, does it?
If you solve the equations, it does not.
I mean, this equation is weaker than crossing, isn't it? It's implied by crossing symmetry, but
yeah, this is just one equation. That's true.
So presumably, I mean, if even in a non-unitary theory, if you write down a bunch of OPEs randomly, they won't satisfy crossing.
Yes, that's true. That's true.
So crossing
it would be very hard to analyze. To discuss that,
Yeah.
we would have to consider all possible set of 4-point functions and whatnot. So
Right.
indeed, it might be that if you try to consider all the constraints at once, you would not be able to solve it.
Right.
But right now, this is not how we do things. We take it one step at a time, and we try to get as much mileage as we can out of one crossing equation, then add another one, and so
Right.
forth. So this is the point is that, so these equations, if you have one solution to cross, if you have a set of solutions to crossing, you can always add them up, right, to get a new one. So any affine linear combination of solutions to crossing is still a solution. So, but this tells you that there are special corners. So if you think of a convex space, right, in general, there will be some special corners, and then every point inside is a combination of these corners. So these corners, they will be very special. These are the corners, they saturate bounds. And they have special properties because their spectrum is very sparse. And so the intuition is that you can have these sparse solutions even in the non-unitary case. But then it doesn't make sense to add them up to get a convex bounded space.
So, sorry, Miguel, can I ask you something? Maybe here for the case of non-unitary theory, it makes more sense what you were mentioning at the beginning, like the study of higher points correlators, no?
It could be. I mean, I don't know. I don't
in
know
the sense that in one correlator you already put several crossing relations. I mean, if you want to study a 6-point function, let's say, you already have more crossing of more operators inside. So there are more OPs that you can take. You will start having operator with spin very soon.
Yes, absolutely. That's true. Yes. It could be that that's the way to proceed in the non-unitary case. So the only method that I know right now, it uses 4-point functions, and the idea is that you truncate this equation such that so you can think of this equation as an infinite set of equations for an infinite set of variables, right? And so what we're going to do is let us truncate. So let us consider just a finite subset of constraints, say n. Okay. And for non-unitary theories, what you try to do is you will try to solve these n equations just using a handful of variables. So then it's just a set of n equations for n variables, and you might hope that you can get a solution. And so this is the only way that I know in which you can bootstrap these non-unitary, but it doesn't work very well. So this is known as Gliozzi's methods. And there's some variations that are developed with Chiral Shok, but you know, it's still not clear if it will work out well in practice or not. But okay, so let me move on. So let me just say, if the feasibility problem can be generalized to the case where we have many correlation functions. So in this case, you ask for a family of linear functionals, omega p. We call that p labeled the number of crossing equations. And now you're going to ask that when this functional acts on these matrices, so recall that these were matrices, they were dotting into these vectors of OPE coefficients. You're going to demand that this linear functional acting on this matrix gives you a positive semi-definite matrix. Okay? It's clear why, because if you have these conditions, then when you act with the functional on the crossing equation that we had before, so you have these vectors of OPE coefficients which are dotting a positive semi-definite matrix. So again, you get something which is strictly positive, and so crossing cannot be satisfied. Okay, so instead of linear constraints, now you have positive semi-definite constraints, so that some matrix will be positive semi-definite. And this is the most general case. So this problem of constructing such a functional subject to these constraints is known as a semi-definite program. Okay, so it's just an optimization problem, a well-known optimization problem, where you have some typically linear objective function subject to these positive semi-definite constraints. So of course, we cannot solve this problem analytically. If you give me some set of quantum numbers, you know, I don't know, in general, to find the functional analytically will be very hard. However, there are standard algorithms for solving these problems numerically. But the first step that they need is that we need to look for these functionals inside a finite dimensional space. Okay, so I'm asking, do there exist linear functionals? But in practice, I cannot look at all of them. I have to look inside some finite dimensional set. And so this is equivalent to the requirement that we cannot look at all the constraints of crossing at once. We need to discretize. And so the simplest way in which you can do this is just you take the crossing equations, which depended on Z and Z bar, and now we're going to Taylor expand them. And we Taylor expand them to some finite order. And so this will give you a finite set of constraints. You can think of Taylor expanding as acting with some basic functionals, the functional which is just the derivative and evaluation at a point. So you were going to look for a functional inside this space. You're going to look for a function which is a finite dimensional combination of derivatives, okay, acting on the crossing equation. This is usually how it's done. So once you've done this, then the state-of-the-art solver of these problems is called SDPD. This is something that was developed by David Simmons-Duffin and later with Walter Landry. And by now, there's many other packages that go around that allow you to do various things. So this is a package that allows you to do these computations with arbitrary precision. It takes advantage of the specific characteristics of the Bootstrap semi-definite programs and so on. It's parallelizable, etc. So as an example, let me give you a very famous example of the feasibility problem, which is studying the 3D easing. So here you just consider the constraints of correlators of the spin and energy field, so sigma and epsilon. And what you find is that in a very large region, you can always find these functionals, so there can be no solutions to crossing. And then there's a very small region where you cannot. So this very small region where you cannot is feasible. And so it's a very small island. So it's this island, when you zoom in, it looks like this. And so for comparison, the Monte Carlo results are here. So these results, they're old by now. They're like 4 years old or something. And they could be substantially improved because the algorithms work better now, that this SDB package works better. So we could push to higher order truncations, meaning that you can get more constraints from a single correlator. So the constraints will be stronger. And we can also push it now to have more correlation functions. So right now, only spin field and energy fields have been included, but you can add, you could now add constraints from other correlators, maybe even the stress tensor, for instance. That would be a good choice. No one has done it, but I mean, at some point, someone will be motivated to do this. The other remark is that if you sit at the edge of the allowed region, where the feasibility problem, where you can just barely find the functional, or otherwise, if you're inside the island, you can also optimize, you can maximize some OP coefficient or something. It turns out that it's possible to find a full solution to crossing, a full solution, sorry. Meaning that you know not just these coefficients, but you also know the CFT data that goes inside the correlator. This is an approximate set of data that will solve these truncated equations. As you increase the size of the truncation, this CFT data seems to converge to something. So again, this was done already several years ago. It's not known whether this island will ever shrink to a point as we increase the numerics, given a finite number of correlators. My guess is that it won't, but this is not settled. Probably not. Again, if 3D easing is a chaotic CFT, what does this mean? It means that we expect that the 3D easing CFT at high energies, the spectrum will just look like random. There will be an exponentially growing number of operators. So to me, I don't see how we could ever get this by using this extremal functional method with a finite number of correlators, but I could be wrong. What we do expect is that as we include more and more constraints for more and more correlators, we'll get systematically better and better approximations to the true easing spectrum up to arbitrarily high energies. The problem is that when you start adding more correlators, then you start running into other kinds of difficulties, numerical difficulties that you need to overcome. So this is better seen in a recent example where people studied the O3 model. Okay, so now in the O3 model, these people studied by bootstrapping the correlator of the elementary field that's charged under O3, and then the singlets that you can build out of this field, and also a traceless symmetric tensor that you can build out of it. So there are these three fields, phi, s, and t, and we're going to bootstrap the set of correlation functions involving these three fields. And with a lot of work, you get this very nice region here in black, and this cube is Monte Carlo results. And so if you look at the scale, you see that the scale is very small. So just to find this region is not obvious, right? You're doing some computational search inside this three-dimensional space, and you just have to do by trial and error, where can I find the functional and where can I not find the functional, right? So you have to do this search. And in fact, it's, well, I'll mention it in a moment. Let me just mention something nice about this result, which is that inside this region, you can, now you can optimize something else. So for instance, you can establish a bound on the leading rank for a charged scalar, and you find that it has to be relevant. And so in this way, the Bootstrap has proven now that the O3 model is unstable to cubic anisotropy. And you see, look at the precision. This is, you can get this bound with 6 digits accuracy. This is just to show you what's the current state of the art of the problem. Not only you do this scan in this three-dimensional space, then you can get also this very accurate bound, sufficient to establish this result. So what are these problems that I was mentioning? The problem is that to get these bounds, then they require you to do some natural assumptions, which are actually hard to impose numerically. For instance, something that's allowed by the crossing equations is that you can have multiple copies of the same operator, meaning operators which share the same quantum numbers, but which have different orientations in OPE space. Okay, so they will have different couplings to the external fields, but they will have the same quantum numbers. So obviously, usually we don't want this. We want to say, for instance, there's only this relevant scalar that appears. There cannot be multiple copies of it. And in practice, to do this, you have to impose it by hand, and you have to scan over these different orientations in OPE space. So actually, to get this plot, you have to do a scan over this this parameter space, which now involves 7 variables. And again, a priori, you don't know where these numbers are. Maybe you have just a rough idea. So how do you do this? So for these works, it was done with some clever algorithms that were sufficient for these purposes. But more recently, there's been a nice idea called the Navigator Function. So what is this Navigator Function? So this is basically a clever algorithm for searching in these high-dimensional spaces. What you do is that you take this feasibility problem and you modify it in a certain way such that it's always feasible, but it has a special objective function. So you need to optimize, and then this objective function gives you a value. This function is called the navigator. And this navigator function has the special property that it will be positive or negative when the unmodified problem is either infeasible or feasible. Okay, so for instance, I showed you this island for the 3D easing before. Okay, so now in this modified fashion, basically the problem is always feasible, so there are always solutions to crossing everywhere. But then this navigator function, usually it will be positive. So you know actually that in the unmodified problem, there are no solutions. However, there's this small region here in white where this navigator function is negative. And so in this case, you know actually that the unmodified problem, you would not be able to find the function. So there are solutions to cross. So the advantage of this is that you have this continuous function to play with. So now, after you sample the function a few times, you can see where it's positive, you can compute its gradient, find out where it's going, and you can try to find the regions where it becomes negative. So it's easier to do this search, okay? So now you just have to minimize this function, which is easier than to just randomly sampling points in this high-dimensional space. Questions about this? Okay, so now let me a bit switch gears and talk about what I would call kinematics from dynamics. So let us go back to the simplest case of a single scalar correlator. Okay, so we had this crossing equation. So the crossing equation presents infinite variables for infinite constraints. So a priori, it's very hard to solve, but we know that it has a very simple solution. The solution, the correlator looks like this. So it's just a sum of 3 terms. These 3 terms are basically Wick contractions. And we know how to compute the conformal block expansion of this correlator. It's also very simple. It contains the identity, and then it contains an infinite tower of operators whose dimensions take this form. And so this solution is known as a generalized free field. Its generalized free fields are basically like free fields, but where the scaling dimension is not the usual free one. It can be larger. If you want, it's the CFT that you get if you consider a free scalar field in EEST space, and then you do holography. The boundary correlators that you get will look like this. So we know that this is a solution, and so we would like to understand what does this solution teach us about the crossing equation, because it's so hard just to find one solution. We have this solution. Can we use it to our advantage to learn something about general properties of the crossing equation? Well, in fact, it's even this solution, it's hard to check that it is a solution, right? If I just give you this data, how do you check that it's a solution? The only way that you have to do it is that you put this into Mathematica and you add this up to some finite n, and you see that this equation is getting approximately satisfied, and it gets better and better satisfied. But to prove rigorously that this is a solution is hard. So one idea is, can we maybe rewrite the crossing equation in a way that this will obviously be a solution? But how can we go about this? So one idea is that really this crossing equation has different representations corresponding to different choices of functional basis. So one basis is just point evaluation. It means that the constraints of the crossing equation are just the constraints that you get by evaluating z and z bar at various points. Okay, this is clearly, it will give you a complete set of constraints. But there are other bases. For instance, I told you that a different way of doing it is just to Taylor expand around a given point. You can take the crossing equation, you can Taylor expand around a given point, and if you keep expanding, this will also give you a complete set of constraints which are equivalent to the original crossing equation, right? So in one case, the functional basis was just point evaluation. In the other case, it's the functional basis just taking derivatives. In general, you might imagine that you can smear against some kernels, and this might also provide a complete basis. Okay? So the message is that each of these bases is obtained by acting with a complete set of linear functionals. And what we want to do then is to construct one of these linear functionals, a set of such functionals, such that the generalized free field will obviously be a solution. So to present the results, let me simplify things a bit at first. So let me just restrict kinematically to the line. So instead of considering Z and Z bar or W and W bar, I'm going to set them to be equal. And I'm only going to use the constraints of SL2R, which is the 1D conformal group. But I'll show you how to generalize this in a moment. So in this special case, then you can prove the following. You can prove that the crossing equation that now looks like this. So these are the OP coefficients squared. There's no spin because I'm in one dimension basically. And the claim is that this crossing equation is completely equivalent to the following, demanding that these sum rules are satisfied for all linear functionals omega inside a set SB. And this set SB is made up of a basis of linear functionals, alpha n's and beta n's, okay, where n ranges over integers. So satisfying the crossing equation is the same as satisfying this countable but infinite set of equations where omega ranges over these functions. And I'm going to tell you the properties of these functions. So what are these functions? These are functions that you can obtain, again, by smearing the crossing equation against some special kernels, which you can construct explicitly. But the point is that these functions, they have some very nice properties, namely that they satisfy some duality conditions in the following sense. So these alpha functionals, they have the property that when they act, excuse me. So that when they act on the scaling dimensions appearing in the GFF solution, they are a Kronecker delta. When they act on the derivative, they just give 0 basically. And the beta functionals, they give 0 for all these deltas, and they are Kronecker deltas when they act on the derivatives. Okay, so what is the point of this? So this is just to give you a picture. So basically, for instance, the beta functionals, they look like this. Okay, so they have double zeros so beta 1 will have a simple 0 at delta 1, and then it will have double zeros at the other deltas, and so on. Okay, so
sorry,
let us.
Miguel,
Yes?
can you say again where you got this alpha beta functionals from?
Well, it's
So and that this is an exact duality, what you wrote there, or
yes,
what are
so
used the Taylor expansion of your crossing equations to get them?
no. So this is an exact. So this is there exist functionals. The functionals, they are defined by the action of some kernel. So you have to integrate this f delta of z against a suitably chosen kernel that is known. Okay, that we need to construct. If you choose this kernel appropriately, okay, then the resulting functional will have these properties. So basically, you demand these properties, and this allows you to fix these kernels. So a general linear functional is just the integral of some kernel against this f delta, right? This is the most general linear functional that you can write down. Okay, so point valuation is just the kernel will be a delta function, Taylor expansion is delta prime, whatever. So in this case, the kernels, they are more complicated. There are some functions. And if you choose these functions carefully, you will find that the functions, when they act on these functions, they have these properties. Okay, and when you plot them, they look like this. But these are explicit known kernels that you can write down. They have all been constructed. I'm just not telling you what they are. So now let us check that the generalized free field is a solution. So we want to check that this equation holds, okay, where I'm plugging in the GFF spectrum. And so the claim is that checking this is equivalent to checking that the sum rules corresponding to all these functionals are satisfied. Sorry, it should be delta here, not m. No, okay, it's n. Here it should be m. Sorry. Well, so how do we check that these equations are true? Well, it's trivial because of these duality conditions. You know, you just get a bunch of zeros. And in fact, these equations, they just collapse onto these ones. So the equations for the alphas, they tell you that these coefficients an have to be equal to the action of these alphas on the identity. Okay, so this is, if you want, this is a definition of what the OP coefficient should be. And the only checks that you need to do is that these beta functionals, when they act on the identity, they have to be. And this you can just check once and for all, and that's it. Okay. So okay, so now we have this very nice functional basis that is specifically dual to this special solution to crossing. But let me emphasize that again, this is a general statement. Okay. This is true for any solution to the crossing equation. We've constructed these functionals such that they have these very nice properties. Okay. But this is just a statement that any CFT has to satisfy. So if you want these functions, they capture the crossing constraints from the perspective of the generalized free field solution. But they are completely equivalent to the original constraints. Okay. So it's a bit like taking a Fourier transform. When you take a Fourier transform, you are using plane waves. Plane waves are solutions to the wave equation, right? So the free wave equation. But we still use the Fourier transform in general settings, even where you don't have free theories, right? So here it's the same logic. It's like a bit of a fancy Fourier transform. So the nice thing is that these functional sum rules, they will imply bounds because the functional actions, they have nice positivity properties. So for instance, you see that the functional actions, they are positive here. And so since the sum rules involve positive OP coefficients, then you get very nice constraints because this equation being 0 requires that the negative pieces cancel against the positive. The functions, they know about this GFF solution. And in particular, this means that they automatically encode the correct high energy asymptotics. Basically, because the asymptotics of a solution to crossing are universal on average. So basically, roughly speaking, they all have to look like, every solution to crossing has to look on average like a generalized free field at high energies. And so these functionals, they nicely allow us to decouple the IR from the UV in the crossing equation. And this implies that this is a very nice basis to do numerics, since the results, the low energy results that we are interested in, will converge very fast in the numerics. So as an example, let me just show you some bootstrap bounds that you can get in the case of the 3D easing twist effect, which is a special B = 1 CFT with O2 symmetry. And so what matters here is that the black dashed dots are the traditional bootstrap analysis, which uses derivatives. And here I think it has 60 components. And then the black and red dots are using these new fancy functionals. And actually, this plot shows two different results with 16 and 40 components, but basically the results converge immediately. So the results, they all lie on top of each other because the minute, so there's basically no difference between using 16 or 40 components down here. And they're both a lot better than this 60 component result with derivatives. So basically, this is really the way to do the numerical bootstrap. It's to use functionals like this. So just to come back on this statement of universality. So this might seem a bit hand-wavy, this statement that on average, all solutions to crossing have to look like GFF. But the functionals themselves, they tell us this. They express this universality property as rigorous bounds on the OP density at scaling dimension. So these bounds, they look like upper and lower bounds on the OP density. So the OP density is this A delta. This A delta free is the OP density of a generalized free field. And then you have to smear it against some simple kernel. But basically, this is telling us that in a bin, in a very small bin, you see a bin of size 1 in scaling dimensions, on average, the OP density has to be equal to that of a generalized free field. It's bounded from above. and it's also bounded from below. Okay, and so these results are obtained by using these functions.
And these bounds are again using unitarity, or that's general?
It's using unitarity. So basically, you have these sum rules that have to be satisfied. And so if you choose omega, for instance, this functional alpha 2, then when you plot the functional, you see that it has a very small negative region here, and then it's positive here. And so the positive contributions have to cancel the negative region, but they cannot be larger than the negative region. So this gives you an upper bound. For instance, the quantity here cannot be larger than whatever goes on here. Okay, so it follows from these sum rules. But it's crucial that these A deltas, they are positive. These A deltas are the OP coefficients squared.
Also, Miguel, you have about 5 minutes left.
Okay, so in higher dimensions, there is a similar story. You can construct bases adapted to generalized free fields. But okay, I don't have time to explain in detail, but there's some ambiguities in the choice of bases that in higher dimensions that have not been fully resolved. And it's not clear what's the best basis that you can use to do numerics. The functional sum rules can also be related to a dispersion relation for CFT correlators. So these positivity properties of the functional actions, they follow from this expression for the CFT correlator. You can express a CFT correlator in terms of its double discontinuity smeared against some positive kernel. And basically, if you expand this relation in powers of Z and Z bar, you recover the functional sum rules that I wrote before. Yeah, I have to go very fast. This is related to the Polyakov bootstrap, which I don't have time to review. Let me mention that these functionals, they're especially well adapted to do perturbation theory, basically because they have double zeros at the dimensions of generalized free fields. So when you deform the spectrum, these functionals, they will kill almost all contributions to the crossing equation. And so you can solve the equation order by order. So the intuition is that either using functionals or using this dispersion relation, you are encoding the correlator or the CFT data in terms of its imaginary part, like you do in scattering amplitudes. And in scattering amplitudes, there's this well-known unitarity method that allows you to bootstrap higher loops from lower loops. So here it's exactly the same logic. You can also use these sum rules to obtain bounds on the coefficients of effective field theories in EEST, but this I think will be reviewed by Simon in his talk. This I will skip entirely, and let me just discuss a bit the outlook. Okay, so what's in the near future for the bootstrap, at least from my perspective? I think we are very close to getting effective solutions of the d=1 crossing problem. This is because there's basically no spin to deal with, so all these kinematic complications are absent. We know that there are efficient functional bases that makes the numerics converge very fast, and this basically means that we can push to have large numbers of correlates. We can bootstrap, I don't know, maybe a set of dozens of correlators at the same time. And there are many nice candidates that can probably be solved or effectively solved very soon, like the long-range Ising model, or line defects like the Wilson line in n=4, or 2D QFTs in EEST. So I think in the near future, we'll be able to do this. Also in the near future is much better numerics in higher D. To do this, we need to settle this problem of obtaining good functional bases in higher dimensions, which have good positivity properties. We need better algorithms for semi-definite programming. And with this, we'll be able to push to larger numbers of correlators, tackle problems like bootstrapping 4D stress tensors, and so on. And again, we'll be able to get effective solutions of models such as 3D Ising, which is almost essentially a reality already in the sense that you already have a lot of information on the correlator of the spin field, but it can still be pushed maybe a bit further. So regarding the, I've already made some comments on here. Maybe in the questions I can come back. So let me just finish with some questions. So my questions are, for instance, what exactly is the bootstrap? I mean, what is it that we are doing here? my idea is that what we are doing some kind of sequence of approximations in the sparsity of the CFT spectrum. And so what we are really doing when we are extracting some spectrum for the 3D piecing is that we are getting the simplest crossing solution compatible with the constraints of one correlator, and then that is compatible with the constraints of 2 and 3 and 4 and so on. So it seems like we're doing some kind of average in this procedure. So we are getting the low energy dynamics correct, but at high energy, we're only getting some average results. So one question is, how can we ever get these expected chaotic UV spectra? Is it just in the limit of multiple correlators, or actually can we get it just with few? What is the link with integrable theories? So another question is, what are these functionals? Why are they positive? Can we construct maybe functional basis dual to interacting CFTs analytically? So this would amount to solving the CFTs exactly. So maybe this could replace our notion of solving the CFT in 2 dimensions. Maybe in higher dimensions, what we should do is construct these bases, and these bases will tell us the spectrum. And maybe finally, so is there a way that we can bootstrap higher point correlators such that we have access to lots of CFT data in one go, like we discussed before? So for instance, in 1 dimension, if you know the generic 8-point function for some scalar, then this actually includes the full set of 4-point functions. You can get all the CFT data from a single 8-point function. So maybe we should look into this, but this will require understanding higher point conformal blocks and the associated kinematics. And I think that's it. Thank you.
Thank you very much, Miguel. So now we have some time for discussion and questions. You can just raise your hand or unmute yourself. So maybe while people are thinking about their questions, so you had a slide that you skipped that was about sparsity and some of the stuff that we already discussed in the beginning of your talk. Can you maybe?
Yes. I'm not sure if it will be super enlightening, but I mean, so for instance, when we checked that the GFF was a solution, positivity didn't play a role, right? We just acted with the functionals on the crossing equation, and we found what the OP coefficients were. And maybe they're positive, maybe they're negative, but it doesn't matter, right? The reason why this is possible is because the GFF solution is sparse. It means basically that there's one piece of CFT data per functional. And this is why you can solve it uniquely. For each functional, you get one equation for one piece of CFT data. A generic solution to crossing will not be sparse like this. In general, the functional equations, they will relate different pieces of CFT data, and you will not be able to solve them completely. So what you can hope then is that there are some of these sparse non-unitary theories which we'll be able to solve basically in the same way by constructing a dual basis of functionals, essentially, that will just solve it completely. Yeah, so it's really, the key is really to demand this sparsity. You cannot have too many operators. Otherwise, there will just be too many solutions, and you don't know which one is the correct one. This is basically the problem.
Are there examples of so this is so sparsity is an input that you make in order to be able to compute something, but is there a reason, like other examples of non-unitary theories that are physically relevant that have been shown to be sparse, have a sparse spectrum?
I mean,
or where is this coming from?
Basically, this is a hope. Some solutions, it would be very surprising if they are not sparse in the sense that I'm indicating, because they are continuously connected to unitary solutions which are sparse. So for instance, in 2 dimensions, there's a family of solutions to crossing corresponding to the minimal models. And in the unitary branch, they are all sparse in the sense, meaning that they all saturate the bound. So if you just continue to impose these sparsity conditions away from the unitary branch, then you can find a solution that looks like a non-unitary minimal model. The question is really how accurately we can get it. Right now, this is the problem. It's how far we can push it to really be sure of this. So specifically, we can get some using the sparsity conditions. You can get a good approximation to the Yang-Lee minimal model, which is non-unitary. The question is really how accurately would we be able to get it?
Yeah, Andres?
Yeah, hi. I want to ask you something, Miguel. So the non-unitary theories are those that have negative dimensions, or you're considering also complex dimensions like happens in the principal continuous series? Because maybe I think the question about non-unitarity that comes from people in this group is about situations that you use dimensions which belong in the principal continuous, which are complex. And I wonder if some of the relations you wrote at the beginning, they apply in this situation.
So this principle of sparsity actually is completely agnostic about, well, is that right? Yeah, I think it's completely agnostic whether, well, all your parameters could be complex numbers. Although probably if you impose, I'm not sure if you'll get something useful out of it. I don't know. I haven't really thought about it. In principle, the method doesn't care about the scaling dimensions that you choose, or everything could be complex in principle, but maybe you'll just get a trivial result in that case.
I was referring
I think for you guys, probably you have other problems, right? Because you probably have a continuous spectrum appearing in the 4-point function. And
Right.
this sparsity
And
principle
also,
really, sorry?
I need a product that's non-positive definite, and yeah.
Yeah, so that goes actually in one of the relations you wrote at the beginning. You had an omega of the conformal blocks, some function of the conformal blocks bigger than 0. So I don't know what that means in case the dimensions are complex.
So what I would
Some at the very beginning
suggest, but again, what I would suggest for these sparse non-unitary theories is that you, instead of thinking about these positive conditions, what you should aim for is constructing functional bases that satisfy relations like this. These relations have nothing to do with positivity. These are just duality conditions. So you choose the spectrum. So the idea is that if you choose the spectrum just right, then you can find a dual basis to it. If you choose the spectrum wrong, you will not be able to. But if you choose it right, then you can find a special functional basis which will satisfy the corresponding duality properties. And yeah, so this has nothing to do with positivity.
Anna?
Yeah, so I have a simple question. So, for example, if you consider a 4-point function where the external operators have different dimensions, that thing is not going to be a positive in general, right? But it should still be crossing. So can, for example, looking at a 4-point function where you have like different dimension operators, can this tell us more than what you already know?
Yeah, of course. I mean, so all these examples I was mentioning with multiple correlators, that the external fields, they have different scaling dimensions. The point is that, so in a single one of these 4-point functions, when you have phi1, phi2, for instance, in the OP, you will not get positivity. But if you consider the ensemble of 4-point functions, then you also get things with phi1, phi1, and things with phi2, phi2. And then you can combine them into these in equations like look like this. Sorry, where is it? Okay, so this is always true. No matter what you choose, you see the external operators here, they don't have to have the same dimension. They can be different dimensions. But the moment that you have one of these quadratic equations, and you know that these coefficients, they are real, then you can play this game with the functions, constructing functions satisfying these constraints.
I see. Okay, yeah, thanks.
Yeah. I think in the things that you guys are interested in, probably the 4-point functions, they will contain a continuous spectrum. No? So it's I'm not sure any of these insights will be relevant, or they would have to be in a very different way, in a different guise.
Putting it around, what insights from Bootstrap do you think will be most relevant for the celestial holography program?
I'm not sure I can give you clues. I have a lot of questions. Maybe the questions will will give you clues. I mean, certainly the Bootstrap, it starts off with basic things like an OPE. So what is the OPE for these celestial CFTs? Does it converge? What is the radius of convergence? Is it just the usual things that we are familiar with in usual CFTs? Also in usual CFTs, we start off with reflection positivity, and this gives you unitarity for the Lorentzian CFT, but in your case, you don't have this. So what is the corresponding condition? I guess it's unitarity in the bulk theory, but what does this mean for the boundary theory? So one really needs to get to grips with these basic things. I mean, as a bootstrapper, for me, the basic questions that I have is, I feel like there's a lot of focus on understanding the symmetries, which are specific when you have massless fields in the bulk and what they imply for extended symmetries for this 2D CFT. But in the bootstrap, kind of, this is not so important, all these things. We can bootstrap equally well CFTs with or without stress tensors, or with or without extended symmetries. What one needs to start with is really these basic properties of knowing the OPE, the rate of convergence, and so on. So even what are the analyticity properties of the 4-point functions that one gets in these celestial CFTs? Right, so in the usual CFTs, we know that for the Euclidean correlator, you know exactly what its analytic structure is. You know a lot about it. But in your case, I don't know, sometimes you get these delta functions. So I don't know if this helps or not.
What would you suggest to do with the delta functions?
What would I suggest?
Yeah.
I don't know. So these delta functions, they arise because, again, you have some continuous spectrum that's getting exchanged, right?
No, there are kinematical conditions for the Mandelstamms. So it comes from the 4-point scattering problem.
Sure, but from the CFT perspective, I mean, so if you do I thought there was some paper where you do the OPE and you understand how this delta function arises.
Yeah, for the OPE, it's not an issue, but I mean, to get the conformal block expansion, I mean, then there's I mean, we have this mixing between C and C bar.
Right. Yeah, I don't know. I mean,
in the OP, we get it from collinear limits, or well, one of the ways to get it. But the delta function appears when you want to compute, let's say, the 3 or 4-point function. That's you know, so well, there is actually a constraint on the dimensions already from the OP. So I don't know if that's standard, because of course the dimensions are continuous, but usually OP constrains due to kinematics the dimensions to follow, let's say, a fusion rule. Okay, but I'm not sure that this is such a big problem.
No, that delta function of the scaling dimensions, I think, is fine. But the kinematic delta function on the cross ratios, that's a bit more more unusual.
And that seems to be, if you compute the OPs, you don't get that one. But when you try to compute the let's say the 4-point function, then of course the kinematics restrict you to have this delta function. So I don't know if you would call it like a problem with a vacuum, for example, or something. So yeah,
and just the only circumstance where I've seen this occur is I'm trying to think. Well, I seem to remember that this delta function is like imposing that z is equal to z bar or something like this. So it's like a line restriction.
Yeah, so it enforces a planarity of the 4-particle scattering.
Yeah.
Momenta.
And they exist actually in the 4-point function. If you go to higher point functions, you don't run into that problem. So that would probably, yeah. So the question probably would go like that. Does a bootstrap always have to start from the 4-point function, or you could start it from a higher point and extract, like you could start from a 6-point function, let's say, and extract all the information? Because there you will not run into that problem.
I mean, you don't even need to start with the 4-point function. You need to start by knowing all the 3-point functions. But if we don't know the 3-point, what we need to know is all the 3-point functions. But the Bootstrap formulates the problem instead of, since we don't know what the 3-point functions are, let us formulate the crossing conditions for the 4-point function, which will constrain the 3-point couplings. And the statement is that if crossing holds for the 4-point functions of all possible operators, then it will hold in an arbitrary correlator with arbitrary numbers of insertions. This is just some diagrammatic argument. It's very easy to see. I
think what Angus wanted to do is to start this program at 5-point, because there we don't have these delta functions, so we don't have to.
Yes, so that's why I said 6-point.
Can you? Yeah. Can you run this whole program at 5 points? I mean, it's more complicated, so that's another question of.
That's why I
No,
said
but let me make a comment here. Can I make a comment?
Yeah.
Five as Mellin transforms, 5-point functions are as bad as 4-point functions and all-point functions. The reason is that the positions, the insertion points of the operators are constrained. Even if you have a higher number of operators, 5 functions, and in usual CFT, the insertion points are not constrained. You can run over the entire complex plane always. But when you do Mellin, when you define celestial amplitudes as Mellin transform, you will always run into this problem.
Yes.
So it's just the distribution, or it's a sort of special thing for 4 points. Then you have a delta function, but for higher points you have the same. You have no distribution, but you still the insertion points are insertion point restrict. So you cannot do crossing or anything like that.
Like that. Yeah. So for 6-point, yeah, I guess there's nothing.
Are restricted. I don't understand. I mean, why is
Yeah,
this
another point. The restrictions come from momentum conservation. Momentum conservation involves the Z's. On a complex plane, you insert operators at different points. Yes.
Yes.
And somehow momentum conservation involves constraint on the Z's. One of them for 4-point function, that the cross ratio of the 4-point function must be real. Okay. And then for higher point function, we have something which is less direct. But there are also there are constraints between various cross ratios. There's more cross ratio when you have more points. But you cannot move the operators on the complex plane as you wish.
Are these the restrictions that the operators they lie on a line?
Yeah, well, yeah. For 4-point function, all operators are stuck. The cross ratio is stuck on a real line.
No, but that's 5 points. At 5 points, the configuration, is it the statement that all 5 operators must also be on a line?
No, that is more complicated. But you have different cross ratio. They have relations. You have more cross ratio. I think for 5 points you have 2. Yes, if I remember. Okay, then you can move them. Then there is a relation between them. So you cannot really change. You cannot really cross.
Right, there should be 5 cross ratios, right? 5 points.
Yeah, the 5-point.
Okay, so but they're constrained. Well, the point is they're constrained.
Actually, I mean, there's a similar problem in CFTs, but it just occurs at higher points. Is that at some point there are constraints among cross ratios. Not all cross ratios are independent because you live in a finite dimensional space, right? So there are these identities. The number of cross ratios naively is whatever n(n-3/2), but this grows quadratically with n, whereas it should grow linearly. So for in one dimensional, the reason why I'm asking for the line is because indeed in one dimension the number of cross ratios is just it grows with n. So there's 1 at 4 points and then 2 at 5 and so on because of these identities. But even for higher DCFT, these identities are there. And at some point they kick in. I guess what you're saying is that for you run into this problem earlier and it's not known how to analytically continue away from this region.
That's the problem, yeah.
More questions?
Let me make another comment then regarding these delta functions. I mean, is this connected to the fact that in a CFT, if you have insertions of, sometimes there are certain non-local operators that you can build that will lead to delta functions in the correlators. But this is just a signal that you are working with the wrong observables. So for instance, if you take the correlator, if you start off with this generalized free field theory, then you can shadow transform some of the operators. And then sometimes you'll get these delta functions.
Here's exactly the opposite.
Yeah.
We start from the delta function. When we shadow, we kind of get rid of the delta function.
Right. Somehow my intuition is that you should do this because in a sense,
Yeah, that's what we do.
while you are considering a scattering problem that starts from the past and goes to infinity. So shouldn't there be two CFTs, one that's in the future, one that's in the past, and they are non-locally related. So
Yeah, that's quite it's something we actually investigate. Yeah, I think Andy was exploring this thing, like different description on the infinite past and infinite future. So there's kind of like something there about two different bases, one in the infinite past and one in the infinite future. It was a recent paper, I think. That,
right.
So that's one, yeah, one possible thing.
So I mean, one comment that I can make, this is an observation that I made a very long time ago. So when you're computing quantities in perturbation theory in CFT using the embedding formalism, so you're doing some ADS CFT computation, you use the embedding formalism, then you end up with these things that look like null momenta. And in particular, so if you're working in ADS4, trying to compute things, sorry, ADS3, trying to compute things in the CFT2. So you have these four-dimensional null momenta, and we know that four-dimensional null momenta, they can be written in terms of spinners, right? And then it's very natural to do a twister transform, where you go from this the lambda and lambda tilde to some lambda mu. And indeed, I remember that for the contact term in ADS, which is just a, well, whatever, it's this D function. If you do this transform, I think you end up with this constraint that Z should be equal to Z bar.
Yeah, that's interesting, actually.
Yeah, I think we'll hear more in that direction tomorrow and on Wednesday.
Yes.
But is there some relation? Because this is a competition, then I know that flat space, you can foliate part of it with ADSs, but
yes,
in your case, it's a bit more complicated.
Yeah. Foliate. Quite interesting.
Anyway.
I don't know if the people who are like Atul or Lionel are around and want to comment on this now or wait until their talk.
Anyway, sorry, this question session got turned a bit into a discussion session, but for me, it's very useful because I'm not sure I'll be able to make it to the discussion tonight. So sorry about that.
Well, thanks a lot for your talk. Are there any more questions before we go into a short break? No? Okay, so let's thank Miguel again and then reconvene in 5 minutes for Tom's talk at 3:30 Central European. Thanks, Miguel.
Thank you.
Yeah, sorry, Andre, about this confusion with the time. I looked at it. First, I thought it was at 2. First, I thought it was at 2, but then I looked again. I said, no, I have to be careful because it's not at 2, it's at 3. And then in the end,
well, it worked out.
Sorry, who's in charge of putting off the recording? Is it me?
Yes.
No. Okay, then I'll do it.
Ah,